Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor here at Foothill College, and it's a pleasure to welcome all of you to this very special lecture in the 10th annual Silicon Valley Astronomy Lectures at Foothill College. These lectures are co-sponsored by Foothill College, the SETI Institute, NASA's Ames Research Center, and the Astronomical Society of the Pacific. And it's a great pleasure for me to welcome everyone here in the auditorium and everyone listening or watching us on the web to tonight's presentation. It happens to be Earth Day today, so happy Earth Day, everyone. And it's very appropriate that tonight we have a talk on protecting the Earth from alien microbes. Our speaker tonight is Dr. Margaret Race, who's an ecologist at the SETI Institute, who works with NASA and the international space community to develop, refine, and apply planetary protection policies to missions to the planets. She's told me that she's actually going to Washington next week to brief Congress and NASA on a major report of a panel at the National Research Council, which she was part of, which took a look at what we should do when we send a mission to Mars to actually get a sample back from Mars. What are the appropriate planetary protection requirements if we're going to bring some parts of Mars back to Earth? And I'm sure she'll be talking about some of these activities. She's also part of an international organizing committee for a hands-on workshop in which people from many countries are going to look at the environmental effects of the Outer Space Treaty in light of what we now know about the possibility of life elsewhere. We have a treaty, which she'll tell you more about, on how we work with other countries in looking at bringing things back and doing things in outer space. And now it's very important to include an environmental impact report in any of these activities. So I think she actually has one of the most exciting jobs in the universe, to think about and act on how we protect our planet from microbes and life elsewhere, and how we protect life elsewhere from microbes and life on our planet. Dr. Race is very interested in education. She's organized and edited proceedings of conferences, served on panels, both scientific and educational. She has a strong interest in communicating science to the public. She's worked both at the Environmental Protection Agency and KQED Television, two of my favorite organizations. And she's organized a number of workshops specifically on the ethical considerations in doing outer space exploration. So it's a real pleasure and privilege to introduce someone to you whose job is really fun. Ladies and gentlemen, Dr. Margaret Race.
Okay, my name is Margaret Race, and I have a confession to make. I'm not an astronomer, as he's told you, and I wasn't sure whether you would acknowledge Earth Day, so I did in my first slide. And it's just by chance that I'm speaking tonight, but I think we would have done it if we knew when we were doing the schedule. So the confession that I have is I'm actually a biologist, a marine biologist, and I began working in mudflats in San Francisco Bay in hip boots. And so it's a long way to go from mudflats to Mars, but in the work that I do, it works. It really does work because what it really is studying our environment. And I began working on introduced species. The species I looked at were mud snails that came literally on the Transcontinental Railroad. When Abraham Lincoln signed the proclamation for having a railroad connect the country, it allowed the gold rush miners to bring foods and things in 2 weeks across the country instead of having it go all the way around South America. So now you had the opportunity to bring in things like oysters from the East Coast. And on the shells of those oysters were things like egg cases of organisms from back east, including mud snails. So I am interested in what happens when you take organisms from one place on Earth and bring them to a new place. And what does that do to the native ecology? What does it do to the functioning of the ecosystem? So I think about environmental impacts in general. Subsequently, I got involved in things like genetic engineering. What happens when you take something you've made in a laboratory and put it outdoors? This is an organism never before seen on Earth. What would be the impact of it? So then when NASA approached me to think about what would it mean to bring back life from Mars, it really is an extension. So I am studying the environment when I work with NASA on planetary protection. And when we're studying that environment, it's real easy to study really what our whole environment is, and that's the universe. And we're not the first generation that has been interested in what's out there. But we are the first generation that has really had the tools and the technology to go and look for things and document places and habitats and other phenomena that we see in ways that never before were possible. So we have a remarkable opportunity to perhaps be the generation that can answer questions about whether or not we're alone. Studying the universe is really like a big puzzle. And so we're studying a puzzle one piece at a time. And I'm over here with the biologist, and the astronomers think about something else, the cosmologist, the paleontologist. All of us have our methods, all of us have our approaches. And we are looking at it, and if you think about how you do a puzzle, you might do the corner pieces first, or someone else might like to look at the colors first, or the big picture. And each of us has a different method, but we're all working together on the same picture. Well, for the biologist, my big picture is this one. That's what I'm in this game for. Is there something out there? And is it like us? And so I know that life on Mars, for instance, won't be friendly little Marvin the Martian. And we all start out with some ideas in our head about what's out there. And we have to quickly separate what's the science part of it, what's the fiction and the fun, and what are our dreams. But we're all playing that same game and gathering information that's adding on to lots of other perspectives that we bring to it. So what I want to give you today is an ecologist perspective on astrobiology and searches for life in the universe. And it's really a science and exploration problem. It's just an organized approach to asking questions about whether we're here alone. So astrobiology really focuses on searches for extraterrestrial life out there. And I'm going to concentrate quite close to home at first. I'm going to keep you looking in the solar system. So this is different than SETI, where you're looking out into the galaxy and thinking about intelligent life. We start this game by saying, what is it we know about life? And what might it be like when we go someplace else? And that's where planetary protection comes in, because I know if you move organisms from one place to another on Earth, you can have problems. Stands to reason, when you go someplace else, you'd want to be careful as well. And then I also have bumped into questions because of having to think about environmental impact statements. When NASA or any government agency is doing a proposal to spend our tax dollars to mount an expedition or send up a rocket or whatever, clear-cut forest, you name it, they have to do environmental impact statements. And oftentimes there are state impact statements as well, like we have in California. In those, people get to ask all sorts of questions. And other questions come up too. Is it legal? Is it right? Is it ethical? And those questions come up but cannot be answered with scientific information. So I want to show you how we've gone on to ask some questions and deliberate about policy and ethical and other societal implications. So when we're searching for life out there, people like me, biologists, and folks who are thinking about missions are really searching close to home. We're beginning with what we know about life, about planets. And as I said, we're thinking about the nature of life here on Earth before. That's all we know. Earth is the only planet in this universe that we know has life. So it's the only thing we know about life. And we're constantly doing hypothesis testing. If life can live in these conditions here on Earth, if we find conditions like that out there, could life be there? So there's been a lot of change within biology and our view of the world here on this planet over the past several decades. Those changes have come in many ways from a lot of the research that we've seen and the exploration within NASA. We now view the Earth as a planet. This picture of the globe as taken in from space is just from the late 60s, early 70s, when we got that view of the great blue marble in space. And we understand that Earth is a part of a solar system. We understand that it's part of something much bigger, and that life has a role on that planet, and it's not just limited by an ecoscape or a landscape or a continent. It really, we think about dynamics. And all of that's happened because of a leapfrog between exploring new places, places we would never have thought to look at before because we didn't have the tools or technology to go to. Think of going down deep, deep in the ocean. And we're using those tools and methods to ask questions at the very micro and nanoscale all the way up through the cosmic scale. And what we've got biologically now is a completely different view of our biological living world than we had, say, 3 decades ago. We are finding organisms that have brand new classifications and metabolisms. We find that microbiological life is ubiquitous. Just about every place we look on this planet, we find life, not a little bit of it. When it's there together with lots of it. And there's a huge biomass. We tend to think of ourselves as being what's really on this planet. Ourselves, the trees, the big things. We are dwarfed by the biomass that is made up of microbes. Not only that, the limits to that life have expanded greatly, and I'll show you some examples of that. We find organisms in places where we never thought to look before. And so now what we think of is a planet that is a biogeochemical planet. And you can't just think about life without thinking about all the rest of it. To give you some ideas, for instance, it was only in the late 70s when the Alvin went down onto some of the mid-ocean ridges and found vent communities down deep at the spreading centers on the ocean floor. Things like 6 feet long worms, tube worms, that had no mouth, no anus, just took in nutrients across their walls, living on a base of a food chain made up by sulfur-eating bacteria that eat nothing but sulfur. We're not talking photosynthesis, we're not talking organic infall from up above. They're eating the sulfur that's coming up in these black smokers. Or take a look at thermal springs and pools like this one in Yellowstone Park. It used to be that we'd think that, well, that's the colors that you see in something like Grand Prismatic Spring must be the minerals in the water. Well, think again, because it's actually the bacteria and the minerals in the water. And you can find organisms that live quite happily above 90 degrees centigrade in basically boiling water in thermal pools. You can find organisms like these in the Rio Tinto in Spain that astrobiologists are studying about that live at pHs of less than 1, pH close to 0. Not only do they live in it, they actually make it more acid by living in there. And that is the iron-rich waters. So think about acid mine drainage. Here's another one, the salt ponds flying into San Francisco Bay. If you take those salt crystals and bring them in a lab and be very careful, you can bring to life organisms that have been dormant inside of salt crystals. And you can also go find things like organisms that live their entire life in the cooling ponds of nuclear power plants. They can tolerate radiation of the sort that would kill anything else. So we find organisms in really unusual places. And so where we're finding out about life like that on our planet, what we're thinking about, well, let's think about biological potential. What are the conditions that are out there? And could there be something that is like life here that lives out there? So when we're looking for extraterrestrial life, we're thinking about biological potential that might be there and habitability of that location. And on Earth, as I said, it's the only place we know that has life. And if you strip it all down, what life needs is just 3 things. It needs the raw materials to make up us, the chemical elements on the periodic table, stuff. It needs an energy source to run it. Could be chemical energy from food, it could be bacteria that you eat, could be photosynthetic energy, lots of different ways to get your energy, could even be heat. And it needs liquid water. That's the key, liquid water, not frozen water, not gaseous water, liquid water, which is all associated with life as we know it. And we know that we're going to focus on microbial life in the solar system. We've been out there, we don't see a lot of aliens talking back to us, no Marvin the Martians. So we're looking at replicating entities of any sort, any biochemistry. We know that life can live in extreme habitats and places here. We know that life has certain characteristics that are ecologically and biologically important, whether it's the limits of life, the physical chemical conditions, the adaptations they may have to live there, how do they grow, how do they reproduce. So we start to look at all of those features as we study it. And we're asking the question, could the target body that we're going to have those conditions that would be okay for life? And we'll take it alive or dead. Could be life living there now, or life that's dead. And on some place like Mars, the planet doesn't have plate tectonics. So if it's up there, if there was life and it's dead, we should be able to find it in the rocks. So what we're asking, that's why when we look to a place like Mars, the biologists are still content for the geologists to do their thing and ask, what are the rocks up there? What are the minerals up there? And what am I finding? Because we're looking for evidence of life that could be hinted at by the geology that we're finding. And we're also looking for liquid water. So anything that would give us hints of water, any kind of landforms, or dried up creek bed looking features, for instance, will give us, in any other clues, things like methane, which on Earth is associated with microbes. So could microbes be underground on Mars? And we're saying if we can find it on Mars, then we would find one more example of life, and once you found one, you've found it all over the place. It's a lot like the extrasolar planet game. Once you can find it and measure it once, you know that there's others out there. So for us, going to Mars is a very good place. It's just the next planet out, so it's a good place to start because we can get there. And we've been there from the Viking missions in the late 1970s, although at that time everyone thought that perhaps they were a failure. We went there to look for life, and the answer was there is none. So there was a long time, you see, until the 90s before we went back again, when the small Sojourner rover went up. And that one's about the size of a microwave oven. The rovers that are still going that were launched in 2003, the Mars exploration rovers, are about the size of a golf cart. Then the Phoenix lander, the ones up in the polar regions right there, right on Mars right now, are sending back lots of information. And we have the Mars science lander that's set to go in 2011. And that one would be on the size of about a small Mini Cooper car. So the spacecraft, the rovers are getting bigger, more able to carry around more instruments, go further, so we're getting a tremendous amount that we've used to tell us a lot about Mars as a planet. What we know is if we look at it now, it doesn't look like a good place for life. It's about half the diameter of Earth. We can see canyons and ices at the poles. We can see storms that happen, big dust storms that envelop the planet, clouds, seasons, all the same kind of things we see here on Earth. But it's got an intense radiation that bathes the surface. It's extremely cold and dry, even at the equator in the summertime. It's only like maybe Antarctic conditions. And the atmosphere is 95% carbon dioxide. So it's not going to be a place amenable to life like us. But the more and more that we know about it, the more we can say, well, microbial life and perhaps liquid water up there are clues that say something's up there. So how do we do it in looking for microbes? Well, we search for evidence of past water when we look at a place like Mars. And when the Spirit and Opportunity rovers landed, we looked in the actual soils and sediments and rocks that were found there. And all of the evidence suggests that there must have been salty water ocean or salty water conditions in the past on Mars. These hematite blueberries that were found all over the landing site, in one of them, I think Spirit, I believe, those are on the order of just a centimeter across, no, less than that, less than millimeters across. Those hematite is formed on Earth only in the presence of liquid water. So here's an indication of something that at the small scale that indicates water had to have been there. When we look at the striations and the sedimentary layers in rocks, we know that there was a watery past. We can look at the minerals and determine that it was a salty location as well. We can also see indications of liquid water at a large scale. So this was frosts on the ground in the Viking missions in the 70s. You could see it forming in the mornings and then subliming away. We also have indication of what looks like an icy, snowy pack. And we know on Earth that if you have snowpack, you can have water at the base of it from just the pressure and the weight of the snow accumulation. We have evidence, look at these scales, that's just 200 meters across on this bar, of what look like gullies. Perhaps this is a permafrost that's kind of melted through and come down on some slopes. And when the spacecraft go over it, sometimes they look clear, next time they come by and it looks like it's wet. Although some say maybe that's not wet, maybe that's just a slump or a slide that's caused the materials to look newer, but we have indications that something's going on geologically that seems to be of interest. We have polar ices, we have even glacial features, glacial scale features up there, and here are some of these photographs of the gullies, what look like landslides, what look like muddy deposits. So there's plenty of things up there geologically that give us hints that perhaps there was water in Mars past. And again, if it's not just Mars that we're looking at, but we can look at something like Jupiter's moons, especially if we look at Europa, a moon of Europa that has thick crust of ice with probably a salty ocean underneath it. Here is something that is outside of what used to be thought of as a habitable zone, and now if you think of habitability not as a distance from the sun, but conditions for liquid water, here's something that's got probably liquid water and a salty ocean. So who knows what's underneath those ices? So that means Jupiter and its moons would be a place that we would like to go. And we're finding out a whole lot about moons in the solar system. So if you look back here, in 1997, the number of moons in the solar system was just about 61. If you look at it now, in 2007, over 168 moons have been discovered. So what it is we're going out more and more and finding locations and having a resolution to identify planets, moons, and bodies out there that we would not have been able to see a long time ago. And we're getting closer and better resolution all the time. And here's an example, too, where just recently Saturn's Cassini mission has looked really closely at the moon Enceladus that has tiger stripes down at the polar region. Normally, you would expect the warmest temperatures to be near the equator. And in fact, in this case, we have the warmest temperatures down at the polar region. And when you look at it in a flyby, in the right conditions, you can actually see geysers shooting out into space from this moon that's about 300 kilometers across, and they're going out 150 or more kilometers, and there's signatures for water ice in those. So here we have a body that is a moon that obviously has some water and water ice that is going out into space, and the spacecraft have been able to go through that. So we've got plenty of locations out there that look like they have conditions that would be amenable to life if it were transported out. So that's where, although we haven't found life yet, we keep looking, but that's where planetary protection comes into play. What we want to do is avoid the mistakes that we did in the past. We know that when Columbus and the early explorers came to the New World, they came without any recognition of the germ theory of disease, for instance. And it turns out that more Native Americans were killed from just breathing on from the explorers breathing on the Native Americans as they traded with them and spoke with them. And when explorers came and re-explored the trading routes along the rivers in the decades after they first arrived in America, they found whole villages empty. And it was things like smallpox, measles, and other microbes that we passed along that caused the demise of the Native Americans. So we don't want to do the equivalent of that on our spacecraft. We know that when we start to launch things from Earth, there are microbes on them. So we do our very best and think about where is it we're launching things, how clean is the spacecraft before it goes, and could any of the organisms on that spacecraft survive and grow and perhaps disperse if they got to another planet or body. So planetary protection is a lot like environmental impact analysis. We're thinking ahead about whether or not we might have an impact when we land on a body. And we're avoiding exotic species problems as we go out. And that's where the mingling microbes comes from. It's Not likely that they would spread real widely, but we have to be careful. If microbes got into conditions in a body of water, like the icy ocean underneath Europa's crust, who's to say what would happen to them? The reasons behind planetary protection are very real. In 1967, the Outer Space Treaty was passed, and in it is a section that focuses specifically on planetary protection. Planetary protection is essentially the avoidance of harmful cross-contamination of planets during the time that you explore. And you also want to think about what you would bring back to Earth. So you want to avoid harmful cross-contamination that would be a biohazard to our planet. So planetary protection thinks of two different things. Forward contamination, introducing onto, say, Mars, terrestrial microbes or materials, contaminants of importance that would go on a spacecraft on its way out, or back contamination, bringing back to Earth the biological contamination or life forms that might be on another planet. And so we have to think about how do you translate that statement about avoiding cross-contamination into something that you would do with your spacecraft. It's a lot like asking for clean water or clean air. Clean water, for instance, it's a good goal to have in the Clean Water Act. Well, what does that mean? Fishable water, drinkable water, swimmable water. For what age group? For someone who's HIV compromised or for the average person, and who's average? So you take that and try to use scientific information and turn it into implementable standards. And what we want to do is have a conservative approach. There's a lot we don't know, so we want to make sure that as we make our decisions, we set our standards in a way that we can not make mistakes and then say, oh, we should have made them tighter. And we revise them over time as we learn more. And originally they were written in a way was to protect the science exploration. So mind you, when the solar system, when the Outer Space Treaty was written, it was written at a time when we were in the height of the Cold War. And it was a treaty that was a lot like its sister treaty, the Antarctic Treaty. In those treaties, we said, these are resources for humankind. So science was an important thing, and science really took a priority. No militarization of the resource. Even now, we don't militarize in Antarctica, and we don't elsewhere as well. And so there are strictures about how clean you keep things and how pristine, essentially. And so we are still living with those controls even now. When we do planetary protection, up until now, it's been done all the time in all of the missions that have been going. And we think about planetary protection for robotic missions that are one-way missions. We think about them for round-trip missions, which things like Apollo missions, recently the Genesis and Stardust missions, eventually a Mars sample return mission. And we'll eventually think about them also for future human missions, back to the moon and on to Mars. And as we encounter new bodies and new environments, new conditions, we think about it. What does that mean? And could we go there and not have to worry about having really clean spacecraft? So we're considering the issues as we go along, much like you do an environmental impact statement. So one-way missions, like to Mars, are pretty routine now. We've got it down. We know what the guidelines are. We're really worried about forward contamination control only. We want to launch clean spacecraft so that they don't leave microbes on Mars that might interfere with even our detection of life. If we're going to look for life, the last thing we want to do is take life with us on the spacecraft and then discover it and not know whether it came from Earth or came from Mars. So all the orbiters, landers, and instruments that go are cleaned in clean rooms as they're putting together the spacecraft. We don't know if there's life out there, and so because we don't know, we're going to be careful to protect the planet that we're going to, and also to protect the science that we're doing. We take multiple controls, so sterilization and cleaning all the time that it's being put together. The spacecraft is documented. We document that information, and it is provided to the United Nations through COSPAR, the Committee on Space Research. So we know what has gone to different locations, and even if something crashes. And the good news is most of it are human-associated microbes that can survive a certain level of sterilization and cleaning. So they're the kinds of things you would expect in a clean room. We want to avoid recontamination, so once it's cleaned, we actually seal things up, so when it's launched, nobody touches it, and literally some of the last people that touch the spacecraft and the rovers are the planetary protection folks who did the last assays and sampling. Think of Q-tips sampling against the materials to determine whether or not there's microbes there. And we keep an inventory also, so we know all of the organic materials that are going up to space. When we consider round-trip missions, they get a little bit more complicated. Not only do you have to do all those forward contamination controls, but you want to think about back contamination. So a round-trip Mars sample return mission, which won't happen until about 2020, involves bringing samples to Earth from Mars. And we know what to do because we did that during the Apollo missions. And in some ways, it will be easier now because we won't have people with them. We're talking about launching and returning only 500 grams of sample. That's about a coffee cup's full, a pound. It'll be a 3-year round-trip mission. It'll take over 10 years to plan. We'll have to think about environment, health, and safety on Earth as well as elsewhere. And that's not a minor thing because NASA and the spacefaring nations and agencies have pretty much control. When they launch a spacecraft, it's off on its own. As soon as you come back and you re-enter the Earth's atmosphere, now all your other federal agencies have questions. What's on it? Where are you landing? Which airspace are you traversing? So there's a lot more different agencies that come into play as well. And as I said, the concept is exotic species. We'll be launching to Mars, collecting rocks and materials, so it'll be rocks and dusts and gases, and bringing it back, landing on Earth, and bringing it to containment labs. So we know that we will contain it and quarantine it. Everything that comes back will go into a containment lab, and NASA has already decided it will be a biosafety level 4. That's the labs like you would put in things like Ebola and Marburg and some of the hemorrhagic fever viruses, the kind that are 100% fatal essentially. So that kind of lab would have to be built for the samples to come back to. Cleanliness would be very important too, because those labs are built in order to keep things in. You want to keep any leaks, you don't want anything to get out onto Earth's environment. But for planetary science, here's some glove boxes, and if you can see all of those things pointed out, those are the gloves. When you want to bring back samples and keep them pristine, you want to have positive pressure in those so that if there's any leak, it goes out and you don't get Earth contaminants coming in. So there's a real engineering challenge on how to build both biological containment and planetary science containment, and that's what the engineers are working on. And to build a lab like that will take 8 to 10 years, and the environmental impact statements will be dual. You'll have one for the mission itself, for launching and bringing back materials, and you'll likely have an environmental impact statement just for the sample receiving facility in whosever neighborhood it will be built. So it's not a minor set of background information that has to be combined. Then we get to the question of human missions to Mars or any place else. Should humans be able to go? We've got planetary protection requirements that say no forward contamination. You and I are walking bags of microbes. In us are 10 to the 12th cells that make up our body. In human beings, there are also 10 to the 13th microbes. All of our cells, we are symbiotic organisms. We have microbes in our gut that help us eat our food. We have microbes on our skin. We're shedding things all the time. So humans going to another planet, like this astronaut here on the moon during Apollo, if you look at that aura around, that's the venting of the cooling water from the spacesuit. So even the equipment that we use vents and contaminates along the way. So the question is, if we go to a place like Mars, is it too much contamination if the astronauts are on the planet for a year and living and working and producing waste and using water and all of those things? Is that a problem for the planet in light of planetary protection requirements? As I said, we can borrow from what we use in the Apollo missions and build forward on that. And we've had some workshops, and we've come to the conclusion, yes, you can plan to send humans, but it's a big job. You'd need to think about, oops, sorry, that one's going backwards when I'm, okay. You have to think about protecting Mars when you go. You have to think about protecting the astronauts. What if there is life up on Mars? and it's microbial, and the astronauts breathe it in or eat it. What if you grew food plants on Mars in Martian soil with Earth seeds? Would you have the possibility of a third biology, a hybrid of some sort? Low probability, but we have to ask that. And at what point do you go from calling that an experiment with a plant to now calling it food? The same thing can be said about the ices. We know that there's frozen water ice on Mars. Can you melt it and use it for the astronauts? Could it have microbes in it? So we start to run into problems that have an impact that are not only planetary protection, but also astronaut health and care. So we've got to build all of those together, and the mission logistics mean that planetary protection people are now starting to work with the life support people, for instance. Spacesuits, should they vent? How should they vent? The habitat itself, how do you build that? If you send pieces up there, do you have to sterilize those pieces the way you sterilize spacecraft on the way? How would you construct it before the astronauts show up? What about supplies and food? Food has typically a 3-year expiration date. Think of packages of food. But if it's a 3-year mission and you want to launch ahead of time, by the time you send the food up there and the astronauts arrive, your food is already expired. So now you've got problems like that. And food has microbes in it. What do you do with that? Waste disposal turns out to be a huge problem. If you have, you and I took showers today, flushed toilets, ran sinks with water in them. And if you think the astronauts will be on the planet's surface for a year, that's a lot of waste. How do you immobilize that waste? You don't just throw it out. You've got to contain it. You've got to make sure that that containment works for some number of years. How long? So all of these things have to be thought about. You'd also have to think about the samples that the astronauts would collect, the rovers that are up there. How do you keep that, the samples and the science materials, separate from the lab and living quarters that are there? What would a quarantine be for astronauts on the way back? Where do you put them? What kind of tests do you do? And the other things is psychological problems. There's no early return. Once you launch from Earth, it's a 3-year round trip, just the way the planets go. And so psychologically and human factors research are big considerations. If the astronaut's not healthy and strong and capable of working in the ways that are required by a planetary protection protocol, all the best rules won't translate into good planetary protection cautions. And so we also have questions that get into ethical. You have astronauts going on a long duration flight of several years. We don't send people to anything for 3 years. Even if you're in a submarine, you're down and back maybe 6 months. So we don't know what it's like for people to be separated and living in artificial habitats for that long. And so we don't know what other kinds of problems will come from that. All of those have impacts on planetary protection. So all these things together mean that as we're thinking about planetary protection, we're thinking about the issues of how we do the missions, how we live up to the controls required by a treaty, and we also have to think, what if we're lucky? What if we find what we're looking for? We have to anticipate all the different kinds of possibilities. Right now, if a rover found life on Mars, found fossils, found something, we've got enough cameras up there, if something moved, we'd be able to see it. What if instead we've got samples that have come here and we find it in a glove box in California or in Texas? Or what if astronauts are on the surface of the planet, pick up a sample and say, my gosh, there's something here? What do you tell the astronauts? The protocols for all of those conditions are completely different. You tell the astronaut to put it down and go home. You can't do it. So we've got to think about also, what if we get a SETI message in the meantime? Would that indicate there's life out there, so we would change what we're doing on missions in the solar system? And we know that things can go wrong. What would we do about finding life out there and knowing that accidents can happen? Could there be a problem from bringing samples here onto Earth? Could there be a problem of a crash on the way back, for instance, like we had with the Stardust mission? All of those worst-case scenarios go into the thinking as well. And the societal and ethical concerns come up in the discussion as well. We're thinking about the impacts on future missions of finding life. What does the government get to do? Who gets to decide? What if people start to want to colonize or commercialize or extract materials from a planet? What if tourism gets going to other bodies? All of those things have impacts on the missions themselves and have considerations that are societal and perhaps even planetary protection. All of the impacts on the individuals themselves, questions about terraforming a planet. What if we decide to go there and introduce life on purpose, to grow things more on another planet? Can we do that on a planet that has life of its own? And as I said, all of our laws, all of our religions, all of our ethical systems are based on life as we know it. Some have said that if we find life out there, we're in a brand new ball game. We have to start to rethink everything right from the ground up, and that we would have a potentially cosmocentric view of the Earth. So then we have to say, how would you revise a treaty that's based on life as we know it? And is the planetary protection in the Outer Space Treaty sufficient in light of perhaps finding life? So we're asking some of those questions. All of them fit in under the rubric of astrobiology, which some of you may know is the study of the origin, evolution, and fate of life in the universe. We're asking questions across many different sciences. Where do we come from? Are we alone out here? And what's the future of life on Earth and in space? And we'd have to include in that not just the future of our life, but the future of other life, if and when we find it. So as we go looking all over, we're looking in many different ways. My work so far has been in the solar system, thinking about missions to planets and bodies that are nearby. But you'd have to consider that we're also looking in other ways. For instance, SETI, Search for Extraterrestrial Intelligence, where we're using radio telescopes and listening for messages from intelligent life. What would that mean? What are the implications of that? And we've heard recently about some more finds of really interesting moons that are much more like the size of, or interesting planets rather, that are the size of Earth-sized planets that are perhaps in the habitable zone around some of the stars that are far off in our galaxy. They're also looking with telescopes and finding evidence of these locations that could have environmental conditions suitable for life. And in the solar system, we're continuing to do lots of work, missions. We're looking at meteorites to see whether they have signs of life in them. And we're doing lots of work in the laboratory to see if we can replicate what are presumed early chemical processes about the time that life must have arisen. What is it that causes life to arise? At what point do we go from chemistry to a replicating system? And that's the question that we're asking on origin of life. If you compare all these searches, what you can see is the SETI searches and the extrasolar planet searches, where we're looking for planets that are orbiting stars far off. Those are out in the galaxy. Those are done in indirect methods. They send us signals, but we don't have any of the evidence in our hands. The nature of life that we'd get is different than what you'd get here in the solar system, where it's more likely that we're looking closer to Earth. We're actually doing missions and doing laboratory experiments and doing the same kind of things that we do here on Earth. The nature of evidence is different. It's geological, physical, chemical. We can have it, we can poke it, we can probe it, we can dig in it. And we can actually determine whether or not that life is similar to life here on Earth. That's the big difference. So if we find a SETI-type signal, or if we find that there's extrasolar planets that look like they have evidence for oxygen in an atmosphere or something that is biologically coupled, we can't tell you anything about what it's made up of. We can't tell you anything about its metabolism, its physiology. But if we find life in the solar system, we can bring it here and we can cross-contaminate. And the other thing that's different about this, and we think ahead to societal issues, is that if we find life out in the galaxy, with SETI we know that it would be intelligent and advanced, but it might also be old. These are signals coming from so very far away, light years away, distances across the galaxy that we can't get to in our lifetimes. So we don't know a whole lot about them. If we find life here in this solar system, it is really startling. It's real time, it has cross-contamination, and it has ethical and theological implications that we have to deal with here and now. And it would be life that exists in real time. We would know it and we could have it. So as astrobiologists, as we're looking ahead, we know astrobiology acknowledges a set of principles, guiding principles for how we do our activities, which should be multidisciplinary in concept and interdisciplinary in the way that we implement it. In other words, we're getting everybody together and working across sciences as a part of a team. We're dedicated to planetary stewardship and planetary protection. NASA and the space agencies across the world, and there are like 90-some signatories of the Outer Space Treaty, all adhere to these notions of keeping their spacecraft and their missions clean in ways that protect the other places. We're also very aware of these societal issues, the kind that come up along the way in missions, and NASA is also very, very interested in education and public outreach. So all of those things fit in. So it means that as we do the science and the research of astrobiology, we're mindful of these other things that are complications that the public is also interested in. What we're saying is that science and exploration can lead to new understanding and capabilities, but also problems. And it's not something that everybody likes to think about. I thought it would be a good idea to talk about some of the biomedical advances and some of the things like global change. We can see science in action every single day. Take, for instance, the recent Octomom and her octuplets. It's an impressive example of how scientific advances have been made. We can take those advances in basic science, translate them to technologies and activities that decades ago no one would have ever thought about. But they raise questions that are societal in nature that science cannot answer. In this case, cost of premature children. Who's paying the bill for these? What are the future handicaps for these babies? What are the ethics of making a decision to have it? Some would have religious questions on whether or not it's appropriate to do in vitro fertilization. Others have raised questions about whether those doctors who aided this woman in the in vitro fertilization were doing things that were ethically right. Lots of people have asked questions about taxpayer money. How's this woman supporting these people, these young children? And what we have is a lack of official policies because the science has gone on into areas where we've never had a chance to think about it before because we didn't have the capability. You can think of similar things coming up in the area of global warming. We've got plenty of data talking about the increase of greenhouse gases, the increase in carbon dioxide, and the scientists can measure that very easily. We're documenting the melting of glaciers, seasonal shifts in polar ices when they melt, how thick they are. That has impacts on water supplies, impacts on things like polar bears and organisms that are evolutionarily coupled to the environments that they're in. We've got increases in average temperature, which I think all of us are already feeling even now, and we're talking about shifts in growing seasons, shift in migrations of organisms, crop losses, pest outbreaks, things that have global scale implications. And the sea level rise that we're talking about predicting is something that is debated greatly, but by mid-century, we're talking about property losses, disrupting populations. So some have suggested that as many as 13 million people in Bangladesh would be displaced by the rising seawaters. 16% of the national rice crop won't be able to grow because it'll now be underwater. Likewise, 72 million people in China, tens of thousands of hectares of the agricultural land. So we're talking about the science and technology that we have now is enough to cause planetary scale changes in what we're doing. So it's appropriate that while we can document patterns and think about it and anticipate and extrapolate and say what things might be like in the future, that we ask the questions now about whether it's the right thing to do. And obviously there are not easy solutions. So back to astrobiology, it's not as dire as the other situation, but we've got great strides. We're going many, many more places than we did in the past. We've broadened our perspectives about life, about the solar system, about the universe, and we've got new understandings that apply to life and our place in the universe. that the problems that have come up, for instance, as I mentioned, the Outer Space Treaty, it was written at a time that we paid attention just to the part that has to do with what to do during exploration. Nobody has thought about what to do upon discovery. And so if we find it, we don't have a policy. No one in the world has a policy for it. So what we've got coming up is an international workshop that is starting to say, what should our policy be if we discover extraterrestrial life? And COSPAR, the Committee on Space Research, is actually planning that, and that workshop will happen probably in early 2009. Again, it's something that grew out of the scientific community, recognizing that there are these changes coming along. And this meeting will have lawyers, policymakers, ethicists, philosophers, theologians, and scientists in attendance. And so it's apparent that we need to start bringing in others as well. This past February, we held a workshop at the SETI Institute where we looked at astrobiology societal issues. We began saying it's really important to figure out how to start to address those principles as we go ahead. We had over 40 participants that came for 2.5 days. We had theologians, ethicists, lawyers, artists, political scientists. It was supported by the NASA Astrobiology Institute and also by SETI Institute. We focused on those questions that had to do with astrobiology and the way we do science. And we said, what are the important societal questions that go along with questions about the origin of life, or questions about whether or not we're alone in this universe, or questions about our future? Can we find out what are the multidisciplinary threads of interest among academic researchers in other fields, probably non-sciences, and say, how do we start to have them start thinking about these questions? Can we find out where they can contribute to the dialogue? And can we start to prioritize issues as we look ahead? What we did is looked at the areas that we think are the most important. A whole bunch of our research within astrobiology is looking at the origin and evolution of life. And you don't have to go a week in the newspaper without seeing something about intelligent design, creation versus evolution, and issues that have to do with the origin of life from a religious perspective. It's important for people to turn to their religious leaders. It's another part of their lives, and most people are quite surprised to find that most mainstream religions have no problem at all with studies about origin and evolution of life. So it would be incumbent upon us to work with theologians and others to really track what are the issues that are associated with it. Are there problems? How can we address them? Also, the questions about sustainability of life and being alone, and most importantly, questions about our relationship with Earth life. How do we relate to life on Earth? And how should that help us in thinking about relating to life someplace else? If you think about it, we don't want to repeat what Columbus and the early explorers did. On the other hand, we're not meeting Native American people. We'd be likely meeting microbes. On Earth, you and I kill microbes every time we use Lysol or take an antibiotic. And that's okay. We're not unethical people. How do you think about life that might be different than us? If it's a second genesis, if it's biologically different, does that uniqueness make it somehow special? Scientists can't answer that. That's where we need to have ethicists, theologians, and others come into the place. And then future of life issues as well. We're at a point now when we're going out, and we can go out to moons, we can go out to planets, we can do things in a laboratory that literally can affect our evolutionary trajectory. How do we want to deal with that? So, as I said, as we think about SETI, SETI principles have already been developed. So within the SETI community, they had a set of rules that what we will do if we discover life. That's different than what we have for microbial life. If we discover it, we do not have a set of rules. So we can start to address something in that area. We got into questions that had to do with topics that are not usually a part of solar system astrobiological research as funded by NASA, but questions that the assembled experts felt we really should include as well. Things like near-Earth objects. We know that there are all sorts of meteorites and materials coming in that come into our planetary environment all the time, from small meteor showers on the size, they're coming in every day on the sizes of dust particles. Or you could have near-Earth objects that are the size of a boulder that, if you're not so lucky, could hit your car like it did in the 90s. You could have things that are much bigger, a building-size asteroid that hit in Tunguska in Russia in the early 1900s and wiped out an area that would be the equivalent of wiping out all of New York City or major Washington, D.C. metropolitan area. What do you do about something like that if you know it's coming? And we have the ability now to say, when we've got near-Earth objects like asteroids that are the size of mountains that could come and wipe out an entire planet, should we just sit here and do nothing? Here we have the ability to recognize a threat from outside. It's a natural threat, but it's a natural crisis that we can avoid if we would divert it. Should we divert it? And at what point? There are no plans right now on what to do about near-Earth objects. We know that they can literally wipe out civilization. We also know that they can wipe out areas and make Hurricane Katrina look like a minor problem. What do we do about that? The impacts are likely to be remarkable on humankind and certainly on national or regional interest. And we're asking, at what point do we step in and do something about it? We have the ability to deflect near-Earth objects. We can tell when they're coming. We could send up missiles. We can intercept the asteroids. We can push them away. We can use a gentle gravity tractoring to change their trajectory so that they don't hit Earth. Should we do it? Should we alter the trajectory in order that we save humankind? If one country does it, is that a good thing? If an asteroid is coming to hit in an area in China and the Chinese deflect and it comes over and instead hits in South America, is that a good thing? Who should be the one to do it? Who should be the one to decide? So recently, there was a group headed by Rusty Schweikert and also assisted by people within NASA who study asteroids. They've gone to the United Nations and begun talking about how do we set up a decision-making framework that will allow us to address questions like incoming asteroid hits. It's something that we want to do, but it also then has military implications. It's missiles in space again. Is that okay under the planetary protection or the Outer Space Treaty or not? It raises questions of who's going to pay for it and how much in advance we want to set aside money to do this. We're also, when we're thinking about going to the moon, we're considering what other kinds of things will come up. Not many people realize it, but when Lindbergh went across the Atlantic for the first time, he did it for a prize. If you go to the Smithsonian Institution in Washington, D.C., Air and Space Museum, you can see many of the prizes that were awarded for early aviation competitions. And the Google Foundation has put forward the Google X Prize to encourage private sector exploration to go back to the moon. Here we have Moon 2.0, as it's called, the second wave of expeditions to the moon, this time by private sector, not by government agencies. And there's a radical $30 million prize for the first private sector venture to go to the moon, to rove for 500 meters, and to send back a mooncast, a broadcast from the moon. There's an additional $5 million if they would document an Apollo site or a Russian landing site. Now you get into problems and questions about, is it okay for someone to go over to the iconic footprint and rove over it with a rover? Can somebody go and break off pieces of the Apollo craft that are still up there and bring them home, perhaps sell them on eBay? We're getting into areas where there are no rules. I would imagine if somebody goes up there and gets Alan Shepard's golf ball and brings it back, that would really be worth a whole lot. But we don't have that. That is an area, the moon, that doesn't have any government oversight. What we have is a resource for humankind. Who gets to make the rules? The private sector go up to do whatever they want? Would they have to apply to the provisions in the Outer Space Treaty and also clean things and worry about when they go to the moon what they do? So what we have is already private sector ventures who are proposing things like commercial delivery of private payloads, of government payloads, of scientific payloads. This is already in the works, and they're thinking about developing rockets that could send up modular units, much like the shuttle payload. They're sharing the pricing, they're sharing it in a condominium style, and so their idea is to be sort of like a delivery service that would go to the moon regularly, a bus that could be adapted to moving things from Earth to the moon and back. What kind of rules and regulations go? And already these kind of questions, should humans, the sites of human occupation, be preserved as a historical location? Are they monuments to humankind that we should all think about? Who should regulate them? Can you strip mine the moon and take off resources? Some celestial bodies are seen as sacred to many cultures. Would it be a problem to go there and do things if Navajos, for instance, feel that the moon is sacred and shouldn't be disturbed? How do you get to adjudicate on that one? And what's our relationship to bodies that have life versus don't have life? If Mars has microbes, and that means Mars has Martians, that's one thing. What would it be if the moon doesn't have life? Does that mean we don't have to live by the same set of rules? And who would set the environmental standards? So what we're trying to do right now is put this all together into a workshop report and try to figure out what kind of roadmap we have, what kind of big issues, legal issues, theological issues, ethical issues, practical issues, medical ones, and how do they all fit into exploration. What we've got is, we're in an era right now of exploration, especially in the solar system, and we're perhaps the generation that may find a discovery of extraterrestrial life, if it's out there in the solar system to be found. And we really need to keep a very broad perspective, one that thinks about astrobiology science, but also the societal implications of what we're doing. And we're always a little bit out on the edge. The science is leading the policy. We don't have the laws. We don't have the policies. So we have to turn around and invite in those experts from non-science areas who may have something to say, who draw from our common history, who think about our ethical concerns, who think with us on the science as we project forward, and think about what it means for humans, for other life as we project into the future, and start to concern ourselves with deliberate evolutionary change as we go into space. We know that this will come up in headline news. We know that it's not going to be something that one or two people decide about. And we have to figure out how we will incorporate these issues that are scientifically and technologically driven into discussions and decision-making of the future. So as we go ahead and try to understand our place in the universe, we're doing it one piece at a time from different scientific perspectives. And for astrobiologists, what we're asking is the simple question, do we live in a biological universe? Are we alone? And what would it mean if we're sharing this universe with others? We're asking whether life can be out there in many, many different places. Basically, if you get the right ingredients out there in the universe and the right conditions, life will emerge many times. So the societal issues affect us here on this planet, and we have a sense that we should do the right things as we go forward, that we should have responsible exploration, but there's no way to look for those kinds of answers. We have to make it up as best we can as we go along. So if we discover that life is out there, we share the universe and life is a cosmic imperative, it's highly significant, scientifically and otherwise. And if it is not out there, if we really are the only life in this universe, that's equally significant, scientifically, societally, and otherwise. So we're sort of in a win-win game, And we have to keep pushing ahead with all of the science, but also be mindful of the issues that we want to address. And planetary protection is one of them, and I can assure you that as NASA and the spacefaring nations are thinking about their missions, planetary protection is very much a part of the entire process. The other pieces are yet to be solved, but we're definitely looking at it. So I'd be happy to entertain questions and talk to you at any time about more on planetary protection and searches in the solar system and the universe.
We'll take questions, and let's get started. Who's got a question or a comment? Right over there.
Okay.
I'll let you take it.
Thank you so much. This was fascinating, but obviously also thought-provoking. I don't quite understand how we sterilize exterior surfaces of returning spaceships. It's pretty hard to do it going out. How do we do it coming back?
Oh, on the out, you can use some of, you don't have to sterilize necessarily the entire spacecraft on the way back. So for instance, on Mars sample return, the samples will get returned, but not necessarily the whole spacecraft. So you can dock in such a way that your sample gets put inside of something that is sterilized or contained. And then on the way back, the spacecraft may continue flying by and only a small portion of the sample comes back in a small vehicle that brings it down. So that you don't, and also out in space, the spacecraft itself is going to be bathed in radiation, so there's a certain amount of sterilization that happens out there. So on the return, you're bringing back the samples only, not the whole spacecraft.
You talked about several conferences that have been held and another one coming up in 2010 where you get all these cross-disciplinary people coming in to discuss all the issues. I'm wondering how much common ground people find and how much agreement versus wild disagreement you encounter.
I'm totally amazed. Now, I can start with the disclaimer. I am not a NASA employee. I come into this in a way that allows me to say whatever I see. And what I see makes me feel very good. It makes me feel good because I see a democratic process working. I see an agency, a government agency, looking ahead and asking about missions and activities that are going to use a lot of money, absolutely, but will happen a decade or more ahead. And the careful planning and the arguing back and forth and the dissension and the debate and the discussion with the mass media and the public is exemplary, I think. So I know that there will be debates. I know I can get in a good argument with anybody on any of these topics that I want to. But to me, that says the system is working. And so it turns out when you get to these meetings also, when you put the science information out there and start to talk about it, it doesn't take long before there's a real consensus. And on planetary protection, the early meetings were fascinating to me because the geologists came and were saying, you know, I just want my rocks. Give me the rocks. I'm just bringing back rocks. What do you mean planetary protection? And yet, in some of these meetings, some of the geologists became the best advocates of planetary protection. And I can tell you from serving on the committee where the idea came up about this meeting on environmental ethics, it was a geologist who proposed the idea of studying ethical considerations if there's Mars, life on Mars. And then we even got into the discussion, well, do you think about a 100-year time frame, or do you start to talk about obliquity cycles on Mars and geological time? At what point do you think about it? So you get into some really heady things that you can't really answer very easily. But it's tremendous consensus.
Good. That's very encouraging. Thank you.
Mm-hmm. There's also a tremendous amount of data that any one of you can get a hold of. National Research Council reports, all of these meetings have reports, so their information is available. Mm-hmm.
Yes, thank you. I was wondering if you could address any of the findings from the recent Phoenix mission.
Any what?
Any of the findings from the recent Phoenix mission to the polar regions of Mars.
No, I don't have, so the part that I work on is more the science policy part and the part prior to launch. How do you prepare the spacecraft? Once it goes up there, I'm in the audience along with you, watching all the information come back. So
Yeah.
I would prefer not to talk about that. I'm not expert on the instruments and science that's on up there right now.
Yeah, I know very little about the instruments, but I heard that there were some very detailed experiments looking for life-type signatures, which I would be interested in.
Yeah,
Thank you.
sorry, can't help you.
Thanks for your talk. At the near the beginning of it, when you were talking about the ethical, philosophical considerations, particularly for human subjects, impact on astronauts traveling in space for 3 years, and we don't use the example of even in submarines, we don't send people to restrictive environments for long periods of time. Something just pinged in my head, and I thought, well, sure we do. We send people to prison for long periods of time. I have no statement about that other than, isn't that a curious thing? I wonder if, in taking in these ethical considerations for all these things, there's research done with willing participants who are in prison incarcerated for long periods of time, particularly in very isolated situations,
I
that are
think even
useful at all.
within prisons, solitary confinement is considered cruel and unusual punishment if it goes on too long. And I don't think that any prison, I don't know for sure, but my guess is that they don't keep people in solitary for a really long time without, for indeterminate amount of time. And even those people get to go outside for an hour a day and exercise, maybe in the yard all alone. But they do see and hear people coming and going, which would be different than a spacecraft.
Sure.
So we know that there will be psychological effects. There are analog situations we can look at for research information. And in fact, at space meetings, there are huge sections that have to do with human factors and psychology. So that's expertise that I don't have, but people are looking at it for sure.
Thanks.
And I believe it's the Russian and French have just started a mission that will put people away for, I think, 500 days. So it's the closest we've gotten. And so these are volunteers. So now that's informed consent and volunteers. So maybe what it is it's all volunteers anyway with astronauts. Okay?
I might have missed your explanation. My question is regarding Outer Space Treaty of 1967 and contamination. We already investigated the moon of the Earth, and then we have a rock of the moon on the Earth. And I think this rock doesn't affect any environment of the Earth. So what my question is, if we found creature or microbes out of space, and then this 3D allow us to bring it back at this point or not?
The National Academy of Sciences, this National Research Council, took a look at the question. And at this point, what we can say, we don't know for sure if there's life up there, so we should assume that there could be. So everything about the design of our handling assumes that there is life in the sample, even though the probability is pretty low.
Okay.
And the other thing is that says if you're going to bring it back, the next, perhaps the most important question is, can you? Technologically, can you bring it back and do it safely? So that's what the early workshops that we had looked at. What we said is, if I had rocks here on Earth that arrived tomorrow, can I handle them? And so we brought in people that included U.S. Department of Agriculture, EPA, Center for Disease Control, all the government agencies, and said, keep wearing your government hat. Is it legal? Yes. And they could have an interagency committee. And is it safe? Do we know enough? Is it legally appropriate to do it? And the answer is yes. We know containment very, very well. We do it all the time. Every hospital that you go to could kill you with all of the microbes that are there. But we know how to contain things. We know the protocols for handling things in a laboratory. And so we would make sure that we're carefully designing the labs so that the workers are safe, but also that material doesn't get out. And so there's a whole set of criteria and protocols that are set up so that of all of the folks that I have seen address that question, None of them feel that we have any concern about bringing things back. And in the next decade or two, things will get better and better and better because technology is getting better.
Okay.
So,
Thank you.
I have two questions. The first one is, have you considered bringing samples from bodies outside the Earth-Moon system back to, say, a moon base or an orbiting space station or something for analysis, rather than bringing them back to Earth?
okay.
And the second question is, when do you consider that you've proved a negative? In other words, you've looked at the samples every which way, and they don't seem to contain any analog of any Earth life. There are no extremophiles. There's no DNA. Nothing that looks like a virus. Do you just say, okay, no life here, or are you trying to twist your brain into a pretzel, trying to think of science fictional scenarios like silicon-based life or things that,
So for Mars sample return, both of those kinds of questions come up. And your first question about bringing things to the moon or to shuttle or something like that always comes up. Number one, we do know how microbes and organisms respond on Earth. So we've got all of our control systems. We know how tissue cultures work and all of that. We don't know how they work in microgravity or someplace else. So if you're going to go someplace else and potentially contaminate it, you'd still have to also think about all of the ways, what would you do for the equivalent of lab rats? What would you do? So to go there and do it someplace else is not easy. There's a tremendous amount of science behind it. And believe it or not, when you look at shuttle or some of the spacecraft that have been up for a long time, it's really hard to keep them clean. In microgravity, microbes and everything go everywhere. So gravity is our friend, as John Rummel, the Planetary Protection Officer, said. So we know how to contain things on Earth, and we know how they respond in gravity. So the idea of putting them someplace else, it's a reasonable alternative, and for a lot of reasons we could say it's not the best solution. So we probably will bring them back to Earth, number one.
Okay.
When do you feel like you've done enough testing to say it's okay to let them out? Now, with the Apollo rocks, when the moon rocks came back, for Apollo 11, 12, and 14, we kept them in very strict quarantine and containment. After Apollo 14, enough tests were done on them. There was an elaborate protocol looking at effects on astronauts, on lab rats, on quail, on fish, on plants, all sorts of things. And there was a preponderance of evidence that nothing was coming up. And it was a reasonable assumption to say we won't have to quarantine anymore. You're right that proving a negative is not possible, but at some point you have enough data to say it's reasonably safe. And
but this would be something that would just sort of a decision that would evolve over time rather than, say, a set of tests that you would run?
The protocol that was developed from a series of workshops, 5 international workshops over 2 years, and then were checked by others and discussed internationally, those set up a set of tests and criteria. In addition, an entire set of discussions were made on what are the criteria for release and who should be involved in those. And so part of this structure on who makes decisions and how do we decide to let the information go public is very important. At what point does it go from data about samples to being called information that is worthy of a press release, for instance? So it's not a matter of holding information back, but up until this time you're measuring, you're looking at mineral signatures or elemental compositions, and that's just data.
Well, I was thinking about going the other way, too, with, say, people settling on Mars. Well, we don't have to worry about, we can bury our waste in the ground because we're pretty sure there's no Martian organisms.
Well, and that's the idea. You can use zonation as a way to do it. If we know that there is nothing in this area because we've searched quite well, maybe that says this should be your landing area.
Okay.
And you will dirty it with people because now you've got all of the spacecraft and habitats and such. But when you go to new areas, you're extremely careful. And so that's what it is. It's a zoned approach, much like we do in Antarctica. So your kinds of questions are exactly what comes up in these workshops, and you start to beat them back and forth and say, can I live with this? Is it legal to do that? And so I can assure you these things have been thought about and are well documented. And if
Thank
you
you.
want some of the documentation, I'd be happy to give you references. Another question?
That was a really exciting lecture. And my question is, I know that humans are carbon-based. Is it possible that there are other life forms on Earth that are not carbon-based?
Very good question. There are some people talking about shadow life on Earth, saying if you go back to astrobiology and think about, okay, we're asking the question, how did life originate? At what point did we go from chemistry to a replicating system? And we're saying maybe it started out with a different set of conditions or a different bunch of ingredients someplace else, so maybe it's biochemically different. It started and went off in a different direction. So some are saying if life is that easy to make, could there also be life on Earth that we just don't recognize? So there have been papers recently to say, what would we do? And so one of the ideas is, could there be silicon-based life? So you start asking these questions. So people are asking that as hypotheses that you might be able to go out and test. So far, we haven't found anything. But they're reasonable scientific approaches. It's a very good way to look at it, and who knows? We didn't find viruses until we sort of stumbled upon them. We never thought about them as a possibility, and is that a living form, or is it not alive? You know, so you get into situations where you find something, and it makes you challenge your very thoughts about biology. So some are suggesting we should look here on Earth as well. And when we look on other planets, we want to make sure we don't just throw at it this thinking about carbon-based life. We have to make sure that we don't do tests for amino acids, tests for DNA. What if it's got something different? So we have to make sure that we're looking at it that would look for DNA and other things, but also look for something else as well.
Thank you.
You've talked about all these wonderful protocols we have for containment, but suppose the parachute doesn't deploy on the return sample. We've had, I think, a case of that in the return sample from a comet.
No, the comet
flyby,
came
and
back
of
okay.
course-
It was the one from the sun, the solar winds that were.
Yeah.
Comet came
Yeah,
back.
and sometimes landing on Mars, parachutes have not deployed.
Right. Okay, so this is where you play within the environmental impact statement process. These are the things that you go through. You go through worst case scenarios. The law requires that you do that. And so you say, what if? And so these kind of things are worked out in a risk assessment with engineers. And actually the parachute one is something that they've thought about a lot. If you think of this, the Stardust mission went out and collected materials that were out there, the solar wind. And it came back, and they wanted to treat these samples very carefully, and so they had rehearsed it so when the parachutes opened, a helicopter was going to come by and collect this thing and gently bring it down to Earth. Well, the parachute didn't open. It had been out there for years, and so it crashed to Earth instead and broke open. There wasn't a problem from a planetary protection point because it was collecting solar wind. There's nothing habitable in solar wind, so there was no concern. But it did wreck the samples. So we have to say, well, gee, that may not be a good thing. So the Stardust mission, when it came back, no parachute. It was made for direct entry. It was made to withstand the impact of hitting the desert in Utah. And that capsule is in the Smithsonian Air and Space Museum right now. It's aside from Apollo, it is the only mission that has successfully come back to Earth that we could go out and collect it. So they're talking about for the Mars sample return mission, you'd probably do it without a parachute. You designed it in such a way that it just comes in on a direct course and can impact. And they know how to do that.
And I understand that when the shuttle Columbia broke up, that there were some living things on board that did survive.
Correct.
The burn-up reentry.
Yes, in fact, the woman who is NASA's Planetary Protection Officer right now is a woman, Cassie Conley, who was from NASA Ames, who actually had some of the experiments on shuttle that did survive. So we do know that organisms can survive really nasty things, and if meteorites are coming in, it's possible that there's microbes on the inside that are coming in the natural free fall, coming into Earth. And they could live through reentry, even the heating on the outside. They're cool enough on the inside. So we don't know for sure whether Martians and other things from outer space might already be here on Earth. We could be descended from them, which is again why we want to keep very clean when we go there, because we want to be able to tell the difference between our biochemistry and anything else we find, especially if we might be cousins.
Two more questions.
Okay?
Why is water still considered an essential criteria for life? Why not liquid methane or liquid ammonia or something like that? Why do we stick to, it sounds like life as we know it still?
Biologically, water is a wonderful solvent. It's a part of life as we know it, and without it, we don't find living systems. So it doesn't mean that you couldn't have life with something else, but life as we know it here on Earth is based on water. Everything we look at seems to have water, and liquid water is part of it, or else it's in a dormant state. And why it is, I guess you'd talk to a chemist about that, a biochemist.
Okay, 2 quick questions. Do you think there's a high probability that we've already contaminated Mars or the Moon with our spacecraft microorganisms from Earth?
Yes. We sent the stuff.
Okay.
And Chris McKay, who's an astrobiologist in NASA Ames, has made some, has done some op-eds and commentaries recently saying, we have contaminated, we know we have. We set the standards based on what does it mean that it's harmful cross-contamination. We know we're sending things up there, but it would just be the local crash site. We don't see things taking off all over the planet. But we're keeping enough record that if we wanted to, we could go back and remove them all. Just like we can go to Antarctica and we can take out old buildings. It doesn't mean you don't build things. It's just you're careful in the way that you do it. And if you contaminated something, are there ways to get it out? Yes, you could move the spacecraft pieces and bring it back to Earth. It'd be very expensive, and you probably wouldn't want to do it. But.
And the second question, do we have a reliable method to, when we're going to these, like to Mars with the science lab to test for life, that we're not seeing some life that we've introduced or brought along on the mission?
When these experiments are designed on what will be done on a future spacecraft, there's a lot of discussion about alternative explanations for various findings, and there's a lot of opportunity to do similar experiments here on Earth to check out things. So there's always debate, and we should expect that. But there's a lot of discussion ahead of time on what experiments would give us information that we don't have already, what experiments will push us into areas that we haven't had a chance to get data on.
Thank you.
Let's thank Dr. Race again.
Thank you.
Thank you.
Okay, thank you. Any students, anybody, or especially any students who might be interested in projects, the data and information about these things, either the societal issues or the science, are so readily available and have been written about in ways even at the lay level. So there's plenty of information. Ask on about it. And the questions that you're all asking are exactly the same questions that have come up in all of the meetings that I've attended. It's just the logical questions that you have to ask, and then you go to the science, you go to the law, you go to the ethical systems, and you do the best you can, because we're into brand new areas. This is very, very exciting. So it's an unusual day when you say we need the lawyers. But we do. Thank you.
Thank you very much. Everybody on May 20th.